So welcome back to my channel. So today let's talk about perfect multicollinearity. So how do you understand this term? What is the intuitive understanding of perfect multicollinearity and the consequence of the problem, and how do you remedy the problem of perfect multicollinearity? Okay, so without further ado, let's dive in. Let's talk about perfect multicollinearity. So perfect multicollinearity. So there's another term which is called imperfect multicollinearity. We'll talk about that in future videos. Okay, today is focused on perfect, which is the easier case, simpler case. Right? Perfect multicollinearity means you think about a regression equation, the regression model, and the one regressor is an exact linear function of some of the other regressors. So, for example, you have example number 1. So you have this y equals b0 plus b1 x1 plus b2 x2 plus error. Okay, so you have this subscript I. So perfect multicollinearity only happens when you have multiple regressors in the regression, right? Perfect multicollinearity means in this case x1 is an exact linear function of x2. So that's, you just use a0, indicate an intercept, a constant, plus a1 times x2. So that means x1, x2 are perfectly linear. Okay. For example, you have this regression. If you have this data I1, 2, 3, 4, 5, and x1, x2, maybe this is 2, 4, 1, 2, 3, 6, 4, 8, -1, -2. Right? x1, x2 are perfectly linear. You see, x1 is just a half of x2, or x2 equals 2 times x1. Right? In this case, x1 equals 0 plus a half times x2. So x1, x2 are perfectly linear. Example number 2 could be y equals b0 plus b1 x1 x1 plus b2 x2 plus error, right? Subscript I. Oh, okay. Plus b3 x3 and plus error. And then x1 may be a linear function of x2 and x3. Okay, x2 and x3. So that means x1, x2, x3 are perfectly linear. Okay, or x2 is a linear function. Let me just use a0, a1 to indicate the intercept and the slope, or the constant parameters. Right? a0 plus a1 times x3. Or x1 equals a0 plus a1 times x3. So these are all perfect multicollinearity examples. x1 is perfectly linear with x2 and x3. x2 is perfectly linear with x3. x1 is perfectly linear with x3. So that's different examples. Okay, so if the example number 1, case number 1, case number 2, case number 3. So you see, by definition, perfect multicollinearity means one regressor is an exact linear function of some of the other regressors. So this could be one regressor is the exact linear function of the other regressor, right? Or one regressor is an exact linear function of all the other regressors, or one regressor is a linear function of some of the other regressor. So these are all cause the problem, which is called perfect multicollinearity. Okay, so now this is a definition, and a very, very common or typical example of perfect multicollinearity is called dummy variable trap. So dummy variable trap, I might just briefly talk about that in this video, and then I might have a different video to mainly talk about dummy variable trap. So dummy variable trap, let's just use example number 3. So this dummy variable trap. If dummy variable means binary variable, the variable can take on only 2 values, 1, 0. For example, 1 is female, 0 is male. So the gender or sex is a dummy variable. So dummy variable trap is you have this data, 1, 2, 3, 4, 5, 6. And then you have this y test score, y1, y2, y3. For each student, you collect a value, you collect the test score. And then the student gender. Female. This is a binary variable, equals 1 if the student is a female, equals 0 if the student is male. And there could be female, female, male, female, male, male, female. And then another variable, you can have a binary variable male, equals 1 if the student is a male, equals 0 is a female. And then look at this, for first student is a female, so that's 1 is female 0, so that means this person is male, right? Second student, female 0, this person is male. For third student, female is 1, not male, right? 1, 0, 0, 1, like this. So now if you want to include both of these two variable, binary variable into the regression, you have a perfect multicollinearity, which is also called dummy variable trap. Is y score equals b0 plus female, b1 female plus b2 male plus error. You think about it, right? So let me write it neater. So b1 female plus b2 male and plus error. So you can pause this video and think about it. How is this variable related to this variable? Okay, why do we call this perfect multicollinearity? So you see, for any individual, the value of female is 0, the value of male is 1. For any individual, the value of female is 1, the value of male is 0. These two binary variables actually represent two mutually exclusive and exhaustive categories. So that means you randomly select a person, this person can fall in one and only one of the category. Right? You randomly select a person, this person fall in either a female or a male. Suppose there's no other gender, so no transgender or whatever, so female or male. So in this case, okay, again, so what the relationship between female and male? Can you use an equation to describe the relationship between the two variables? You can pause the video, think about it. The relationship is a female, the value plus male equals 1, or female always equal to 1 minus male. You see, these two variables are perfectly collinear. A0 is 1 and A1 is -1. Again, we're talking about dummy variable trap in the next video, but this video, we're talking about the perfect multicollinearity in general. The dummy variable trap is just a special case of perfect multicollinearity. Okay, so again, perfect multicollinearity by definition means one regressor is an exact linear function of some of the other regressors. Okay, and then let's talk about the consequence of it. So if we have perfect multicollinearity, the consequence is that, using this as an example, the consequence is x1, x2 perfect collinear, you cannot get all the coefficients estimated. Right? Even if you have a data, you run a regression, you run regression y, regress y against x1, x2, and x1, x2 perfect collinear, and then the consequence is that you will not get all the coefficients estimated. Same thing, for example, here. So x2, x3 are perfect collinear. You just include both x2, x3 into a regression. The thing is you cannot get b2 or b3 estimated. Okay, same thing here. You cannot get both b1 and b2 estimated. Why? Because think about how do we interpret B1 here, or B2. So we interpret B1 as the effect of unit change in X on Y, right? The effect of unit change in X1 on Y once you hold X2 constant, right? So we interpret B1 as once we hold x2 constant, the effect of unit change in x1 on y. Same thing for B2. The effect of unit change in x2 on y. You just use this, okay, this delta derivative or first order condition to indicate the effect, all right, the marginal effect of unit change in x2 on y once you hold x1 constant. But the thing is, if x1, x2 are perfect collinear, that means once you hold x2 constant and there's nothing change in x1. Once you hold x2 constant, x1 is also held constant, right? So if x2 is held constant, there'll be nothing change in x1. So that means you cannot get the effect of change in x1 on y because x1 has no change. Okay. Same thing. So if x2, x3 are perfect collinear, and then once you hold x3 constant and there's nothing change in x2, so that means you interpret B2 as the effect of unit change in x2 on y once you hold all the other variable constant. x1 is held constant, but if x3 is held constant and this is the case, and x2 is no change, right? So once you hold the other variable constant and then there's no change in x2, right? So that means you just can't find the effect of change in x2 on y. Same thing here. Once you hold a male constant, right? If the male equals 1 and the female has to be equal to 0. So I just use the dummy variable trap as an example. So expected value of y given female is 1, male is 0. You know that equals b0 plus b1. And now you want to look at the expected value of y given female is 0 and holding male is 0. You want to hold the other variable constant to look at the effect of changing f on y. But the thing is, look at this. F is 0, male is 0, female 0, male 0. There's no people falling in this category. So that means this is no observations, right? No observation available in this category. And then you can't find any value for this expected value of y. So that means you cannot just get b0, b1, b2 estimated. Okay, you cannot get this b0, b1, b2 estimated. So that's the consequence. Okay, so if perfect multicollinearity occurs, you cannot get all the coefficients of regressors estimated. Okay, you might get b0 estimated, but definitely not b1 or b2. Okay, if perfect multicollinearity happens. So the remedy, right, the solution to this problem is very, very simple. So that's why I said that in the beginning of the video that perfect multicollinearity is a simpler case as opposed or compared to imperfect multicollinearity. So because it's very easy to remedy the problem, it's just you drop one of the regressors that cause perfect multicollinearity. For example, in this case, let me use a different color. Which color has not been used? Maybe, okay, this, okay, maybe this color. So using this as an example, you can just drop, let me just use bold color. Use this as an example, you can just drop one of the regressor. Drop x2, drop x2. Okay, you can just drop x2. Okay, let me just zoom out a little bit. So if you have this case number 1, you run this regression y b0 plus b1 x1 plus b2 x2 in the computational software, for example, Stata, okay, or R or Python. And then, but x1 equals x2, for example. x1, x2 are perfect collinear, have this relationship x1 equals x2, okay, perfect collinear. And then the software or Stata will actually do this. Y equals b0 plus b1 x1 plus b2 x1, because Stata knows that. They can detect this perfect multicollinearity immediately. So plus error, and they know that it knows that this is, you know, same thing. So that's b0 plus b1 plus b2 times x1 plus error. You see, you run a regression with 2 regressors, but it turned out that there's only 1 regressor, right? It serves the same purpose of 1 regressor. So now Stata will give you a value for b0. For example, the value is 4, and give you a value for b1 plus b2, maybe 6. And then you have b0 equals 4, and b1 plus b2 equals 6. 3 unknown variables in 2 equations. Of course, you can get all 3 variables estimated, right? So b0 is 4, but b1, b2, the value b1, the value b2, to be determined, right? So that's the consequence. Again, that's the consequence of perfect multicollinearity. And so the remedy, the solution to this problem is just drop one of the regressor that cause perfect multicollinearity. If x2 and x3 are perfect collinear, you can just drop one of the regressor. Right? If you just run this regression and this data, for example, the computational software will automatically drop one of the regressors for you, okay, due to perfect multicollinearity, and then x3 is dropped. Okay, so if you not drop it for Stata, you not drop it by yourself, and the Stata will drop it for you. Okay, it's here. You just need to drop one of the regressor for dummy variable trap, right? Just drop one of the dummy variables. Okay, so this is today's video. Perfect multicollinearity. By definition, perfect multicollinearity means one regressor is an exact linear function of some of the other regressors. And the consequence of perfect multicollinearity is you cannot get all the coefficients of regressors estimated. Okay, and the remedy, to remedy the problem, you just need to drop one of the regressors. I hope you find today's video helpful, and next video is going to be about dummy variable trap, which is a special case of perfect multicollinearity. So stay tuned. Any questions, comments, concerns, please let me know. Okay, any questions, let me know. And thank you so much for watching, and see you next time. Bye.